Having defined discrete sets, we shall discuss discrete structures, objects that we would be seeing or exposing you as part of this course. So we talk about discrete sets. Subsequently, we talk about the structures based on discrete sets, namely cross products, relations, functions, graphs. So in some sense all are relations, but this one is a special relation, this one is also a special relation, and so on. Fine. So we come across relations, functions, graphs when we talk about the subject, say database management systems. The tables in a database is an example of a relation. And when you try modeling problems in computer networks or operating systems, you get to see a special relation called graphs. We come across directed graphs or undirected graphs and so on. When we come across scheduling problems in operating systems, cloud computing, distributed computing, we come across functions. You have so many servers and there are clients waiting for or requesting for a service, and so client should be mapped to which server or which client should be serviced next, and such questions can be modeled using functions. And the base for all of this is something called cross product, and which is defined based on an underlying set which is discrete in nature. Okay. One can also talk about relations, functions, graphs in the context of continuous sets, but as far as computer science is concerned, and in particular this course is concerned, the focus is on discrete sets. Okay. And as you can see, once the definitions are clear, you get to see that as long as the underlying set is clear, you can define appropriate relations and functions independent of whether it is discrete or continuous in nature. But the applications that we come across in computer science are largely discrete in nature, so our focus is on discrete sets. Fine. Set is a collection of well-defined objects. Example, you say set of computers in a computing lab. Fine. Set of students enrolled for MTech CSC. Set of natural numbers, set of leaves in a tree, and so on. Set of trees in a country, and so on. This is a well-defined collection. It gets the name set. We often go for formal way of representing sets, a formal representation. So it is represented as A1, A2, so on up to AN. So this A1, in general AI, may represent a computer if you take this set, may represent a student if you take this, represent a number if you take this, represent a leaf if you take this. So for us, we are not concerned with the underlying set or the application in which it is used when we talk about this formal representation or a formal specification. So this tells you that there are n elements, a1 being the first element, a2 being the second element, and so on. Set could be finite or infinite. So this is an example of a finite set of size n. It could even be a1, a2, dot dot dot, which means this is an example of an infinite set. For example, set of natural numbers is an example of an infinite set. So given a set A, we can talk about its cardinality or size of the set. It is denoted using this. And what is this telling you? This is telling us number of elements in the set. For example, if you take this, there are n elements. Suppose there are 60 computers in the lab, then the answer to the cardinality of this set is 60. Suppose there are 15 students enrolled for MTech CSC, then cardinality of this set is 50. And cardinality of this set is infinite, because you cannot talk about a specific number for an infinite set. And this may be, say, 1200 if a tree is fixed. So given this, based on this, we discuss our very first discrete structure, namely cross product. The term cross product is defined using two sets, namely, say, A and B. And this is also a set. So the cross product of two sets A and B is denoted using this symbol. It is a set. Then what are its elements? Consist of A comma B such that A belongs to A and B belongs to this. So here is a formal way of writing the definition of the cross product of two sets A and B. It is again a set consisting of pairs A comma B, and if you look at a pair AB, then the first element A comes from the first set, the second element B comes from the second set. For example, suppose A consists of 1, 2, 3 and B consists of X, Y, Z, then A cross B has 1 comma X and 1 comma Y, 1 comma Z, 2 comma X, 2 comma Y, 2 comma Z, 3 comma X, 3 comma Y, and 3 comma Z. So as you can see that when we define these two formally, you get to see that A cross B is also defined formally using this definition. And what it says is it consists of pairs A comma B, where A comes from the first set and B comes from this. And you look at all possible values for A and B. And and possible values for A are 1, 2, 3. Possible values for B are X, Y and Z. Now, this is precisely what we are interested in as part of a formal representation or formal specification as far as this course is concerned. So, this may refer maybe a computer in a lab. This may represent a leaf in a tree. This may represent say a student admitted for so and so course, but we are not interested in all that. We abstract out and we just focus on the set. We focus on first element, second element and so on. That first element may be a leaf, that may be a computer, that may be a student, that depends on the application. So the abstraction helps you to bring the necessary focus, and using which you can study other concepts. You can make use of tools and techniques. You can talk about counting problems. You can talk about problems which use this idea or the concept. So that's precisely our focus when we focus on say mathematical abstraction. Okay. Now, having given this, one can talk about something called relation. In particular, one can talk about something called binary relation. So here is the definition. A binary relation R, it is denoted using the symbol R, defined on a binary relation R defined on A is a set such that R is a subset of A cross E. This means such that. So binary relation defined on A is a set, and where is that set coming from? It's coming from this set. So it's basically a subset. Subset is also a set. It is some subset in A cross A. Suppose B is same as A, then one can talk about the cross product for A cross A. And any subset in that is a binary relation. So one can talk about A cross A. So A cross A consisting of elements 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. Now, what is R? R is some subset in A cross A. It could be any subset. Now, R could be empty, and R could be 1, 1, 3, 1. It is a subset in A cross A. So, which means this is an element, this is an element, and so on. And R could be everything. R could be A cross A, or R could be 1, 1, 2, 2, 3, 3. So we come across these binary relations when we talk about database systems, and this may represent a record, this may represent a transaction, so this may represent a field in a table, So it could mean no anything. But as part of mathematical abstraction, we will not get into specific thing like does it represent a transaction, does it represent a field, does it represent a data item, all that. Instead, we talk about 1, 2, 3, we talk about A1, A2, A3 and so on. And subsequently, when you come across a specific application in, say, database domain, you can map this actually corresponds to a set. This is the underlying cross product, and table is actually a subset in this cross product. Therefore, the table represents a binary relation. So the focus of this course is to highlight you these mathematical tools with connection to specific field in computer science. And having seen sets, cross products and binary relations, first thing you must observe is there is a formal way of writing statements like this, and there is a formal way of writing definition of say cross product or relation and so on. Is there a language? Is there a language that teaches you this formalism so that any statement can be represented in a formal way, avoiding English and bringing more math into the representation, and thereby you remove ambiguity, you bring in precision, and it is free from errors. And such language is what we look for as far as mathematics is concerned. So one such language is logic, which we shall expose you to first order logic now, and subsequently we will revisit the definition of cross product, relations and properties on relations. And you see that once you learn such a language, representation of a statement, interpretation of a statement, and does that statement convey a meaning, is there a truth value associated with such a statement, all that makes sense. So what we will do is we shall discuss first order logic, then we shall revisit cross product and relation, introduce some more properties, then start discussing counting problems and its applications in the field of computer science. That shall be our next focus.